Hello everyone, I am Dr. Ahmad Shaffie and I will be your instructor for CSCI 1400 Digital Fundamentals course. In this video, I'm going to give you an overview of our lab assignment. I will start by discussing the importance of having this lab assignment in our course. Next, I will go over the key components you will be working with in the lab, such as ICs, switches, and other essential circuit elements. Finally, I will introduce you to your first lab assignment, explaining what is expected and the task you need to complete. So by the end of this presentation, you should have a good understanding of what is ahead in the lab. Let's get started. Now, let's talk about why this lab assignment is so important. First, it's all about hands-on learning. While theoretical knowledge is crucial, lab assignments allow you to apply those concepts in a practical setting, which really helps to solidify your understanding of digital design principles. Next, lab work is key for skill development. As you work in these assignments, you will be developing essential technical skills, such as circuit assembly, troubleshooting, and using tools like multimeters and breadboards. Moreover, this assignment emphasizes real-world application. Lab work bridges the gap between theory and practice, preparing you for the challenges you might face in professional settings. Another benefit is that it fosters critical thinking. You will need to analyze problems, test your ideas, and come up with solutions, all of which sharpen your problem-solving skills. Finally, collaboration is a big part of this lab. You will often work in teams, which encourages you to share ideas and learn from each other. This collaborative experience is invaluable both in academic settings and in the workspace. So these lab assignments are not just about completing tasks. They are about building the knowledge and the skills that you will serve you well throughout your academic and professional career. In this slide, I will introduce the digital components we will be using throughout our lab assignment. As I mentioned in my previous email, it is important to make sure you have access to these components as we will be using them frequently. Let's start with the breadboard. This will be your primary workspace for assembling circuits. Next, we have LEDs that will help us visualize circuits outputs. You will also need resistors, which are crucial for controlling current flow in your circuits. Another key component is the integrated circuits that we call ICs, which are the brain of our digital logic circuits. To power everything, you will need a power supply that provides consistent voltage. We also use switches to control the flow of electricity in our circuit, and they act like our input. And of course, wires to connect all these components together. In the following slides, I will go into more detail about each of these components, explaining their function, how they are used in the lab, and some best practice for working with them. It's important that you are familiar with each of these components before we start our hands-on work. So let's take a closer look. Let's start with one of the most fundamental tools you will be using in our labs, the breadboard. A breadboard is a simple component that allows us to build and test circuits without the need for soldering. It is essentially a platform where we can easily insert components like resistors, LEDs, and integrated circuits and connect them using wire. Now, here is a question. Why do we need to use a breadboard? The main reason we use a breadboard is for prototyping circuits. By using a breadboard, we can quickly assemble and modify our circuit without permanently fixing the component together, like you see here in this image. This is not only allow us to troubleshoot and solve any problems that may arise, but also enables us to reuse the component in future projects. And simply, this is what we will be doing in our different labs. And the question now, how this breadboard work? Breadboards have lines running all the way down the longest side, which are known as the power lines, because you can plug your power supply into them to provide power to the other components that we have in this breadboard. On the inside, running perpendicular to these lines are the components lines, and these are where you place your components. Here we have a view of a flipped breadboard with the backing removed so you can see the internal structure. As you can see, the breadboard is composed of metal strips that run underneath the hole. These strips connect the component you insert into the holes, allowing the electrical signal to flow between them. The rows are connected horizontally to supply power across the board, while the components line on each side vertically connected for placing components. I am sure some of you are wondering why we call it a breadboard when there is no bread involved. The answer is quite interesting and goes back to the history of prototyping circuits. Before modern breadboards were developed, people who wanted to prototype circuits quickly without soldering would use an actual breadboard. Yes, the kind you find in a kitchen. They would take this wooden board, insert their components, and secure them with screws or nails to create temporary circuits. This allowed them to test their designs before committing to something more permanent. The name breadboard stuck, and although we now use plastic boards with built-in connection, the term still reminds us of those early days of circuit design. Now, let's talk about LEDs or light emitting diodes. LEDs are a powerful and energy efficient lighting solution that has changed the industry. Unlike traditional bulbs, LEDs consume less energy and have a much longer lifespan. An important characteristic of LEDs is that they allow the passage of electric current in only one direction. In terms of voltage, LEDs typically handle between 1.8 to 3.5 volts. As you can see in the figure, an LED has two legs or pins, one longer than the other. The longer leg is the anode marked with a plus sign, and the shorter leg is the cathode marked with a minus sign. Now let's look at a simple circuit with an LED and a battery. In the first example, the LED is connected the wrong way, so it won't light up. Why it is connected in a wrong way? Because the positive is connected to the negative and the negative is connected to the positive. And this is not the right way to connect a LED. This is why I said the LED can only allow the passage of the electric current in one direction. So this connection is not correct. When I flip the battery around, the LED does light up, but there is still a problem. The battery provides 5 volts, as you see here, while the LED can only handle up to 3.5 volts. This excess voltage could damage or even burn out the LED. To protect the LED, we need to add a resistor to the circuit. The resistor will help divide the voltage between itself and the LED, reducing the voltage load on the LED and ensuring it operates correctly and safely. And this is the correct way to connect an LED in a circuit. On this slide, we are taking a closer look at how integrated circuits or ICs are used to implement logic gates. As you have learned in Module 1, there are different kinds of logic gates, with the basic ones being AND gate, NOT gate, and finally OR gates. Let's start with the AND gate. We have two ICs for AND gates, the 7408 and the 7411. The key difference between these two is that the 7408 contains two input AND gates, while the 7411 contains three input AND gates. This is why we have two different models. Next, for the NOT gate, we use the 7404 IC, and it has 6 independent NOT gates. And for the OR gate, we have two options as well, the 7432 for two input OR gates and the 4075 for three input OR gates. It is important to note that the ICs starting with 74 belongs to the TTL family, which stands for transistor logic. On the other hand, the ICs start with 40 belong to the CMOS family, which stands for complementary metal oxide semiconductor. By the way, our discussion for Module 2 will be about the different ICs and the digital logic family. Now let's move and have a closer look at the AND gate 7408. The IC 7408 contains 14 pins. One of the crucial things to get right when working with ICs is the orientation. To ensure you understand the pin configuration, you need to look for the small half circle notch on one side of the IC that you can see here. This notch helps you orient the IC correctly. When the notch is facing to your left, pin 1 is on the bottom left, and the pin number increases as you move counterclockwise around the IC. In the 7408 IC, pin 14 should always be connected to the VCC, which is the positive voltage, while pin 7 should be connected to ground, which is 0 voltage. If we look inside the IC, we can see that it contains 4 independent 2 input AND gates. These are the building blocks that we will use in our digital circuits. Now, let's jump to the next component, the switches, which we will use to represent the inputs in our digital circuits. Each switch has 3 pins. The middle pin is fixed and should be connected to the input of the logic gate. The other 2 pins are connected to either the power supply or ground. Suppose we connect the right pin to VCC representing a logical 1 and the left pin to ground representing a logical 0. If the switch handle is to the right, like you see here, the middle pin is connected to the right pin, which means the input to the logic gate is 1. Conversely, If the handle is flipped to the left, the input would be 0 because we connect the middle pin to the left one, which means the input value should be 0. By understanding how to properly connect and use switches, you will be able to control the inputs of your digital circuits effectively. The last component that we will cover in this video is the power supply, which is compatible with our breadboard. The input voltage for this power supply ranges from 6.5 to 12 volts DC, and it provides output voltage of 3.3 volts and 5 volts DC, with a maximum output current of less than 700 milliampere. Let's break down the key component of the power supply. First, we have the power switch, which allow you to turn the power on and off. Next, there is a power indicator LED, which light up when the power is on, giving you a quick visual confirmation that your circuit is powered. Moving on, you will see the USB power input and the DC power input, both of which can be used to supply power to the breadboard. And note that you can use only one of them at a time. The breadboard output pin that distributes the power to your circuit. And finally, there is an extra output that can be used to power an additional device or something like a cooling fan. This flexibility makes the power supply a very important tool for a variety of circuit configurations. Now that we have learned about the key components we will be using during our lab assignments, let's dive into our first lab assignment. Don't worry, it is going to be very easy. For this assignment, I want you to test and understand the functionality of the 7408 IC, which contains 4 AND gates. You don't need to test all 4 gates, just focusing on one will be enough. You will use 2 switches to represent the 2 inputs of the AND gate and an LED to visually represent the output. Uh, this is the theoretical truth table that shows us how an AND gate works. If both inputs are on or 1, I expect the LED to light up. However, if one or both inputs are off or 0, then the output should be 0 and the LED should stay off. I have also provided you with a data sheet for this IC to help guide you through the process. Take your time, experiment, and get comfortable with how the circuit behaves. For this lab assignment, your deliverable will be a detailed report. This report should include several key components: a problem statement that clearly define what you are testing, the truth table for the AND gate you are testing, a circuit diagram showing how you connected your components, a chips diagram illustrating the internal structure of the 7408 IC, chip requirement and assignments to outline the connections, a chips layout detailing the physical placement on the breadboard, and finally, a discussion section where you compare your empirical finding with the theoretical expectations. I understand there are a lot of new terms here, and I won't be defining them for you now. Your job is to research these terms and prepare your report in the way that best suits your understanding. I will be very lenient with grading this first lab report. After the deadline, I will share with you my exact format and expectations for future labs. So don't panic, do your best, learn as you go, and most importantly, enjoy the lab. Feel free to take pictures of your circuit once it is working, or even record a video showing how changing the inputs affect the outputs. You can include the link to the video in your report and the picture you take for your circuits too. That's all I have for you today. Thank you for watching the video and taking the time to engage with this material. Remember, if you have any questions or need further clarification, don't hesitate to reach out. Just because you are studying online doesn't mean you are alone. You are part of a community with your professor and peers here to support you. We are all on this together, so don't be afraid to ask for help or share your thoughts. Good luck with your lab assignments and look forward to seeing your work. Bye.